Good morning, everybody. It is Monday, March 23rd, and it is probably going to be a snow day for most of us, except for those of us trapped at home because of the coronavirus. Hashtag all of us. So let's get started. Today we're going to learn about radioactive decay and how it compares to the coronavirus. So get out your notebooks and your earth science reference tables, and let's go. All right, first thing you need to draw in your notebooks, something like this. This represents a hospital in which 16 people checked in with the coronavirus. They are all infected. That's why I drew them in red. So these 16 people, they're all infected with the coronavirus. Maybe this guy just got the coronavirus, and maybe this guy just had the coronavirus for 2 weeks already, but they're all in the same room. There's 16 of them. So I'm going to label this image 16 infected and 0 recovered. About a day later, 1 day later, miraculously, 8 of these people have recovered. So now they're in purple. And I still have 8 infected. So 1 day later, I'm going to have 8 infected. And I'm going to draw this in purple. 8 recovered. All right, another day later, 1 day later. Now this is assuming that the recovery period is pretty quick for the coronavirus. Another day later, I'm going to get half of those that were infected over here, those 8 people, half of them have now recovered. So now I have 4 new guys that are newly recovered, and I have 4 that are still infected. So when I add those numbers up, I'm going to get only 4 infected. And now I have, say it with me, 12 people recovered. 12. Okay, so you know where I'm going with this, right? And then my next stage over, in my same hospital bed, my same hospital room, I now out of these 4 people that were still infected, half of them are going to recover. So that's 2 more recovered. So 2 more to my recovery list. Now I have 14 recovered. And only 2 are infected. I forgot to say, this is always 1 day later, people. We're doing things in days today. Another day later, after these 2 people are infected, say with me how many left are going to be infected? Only 1. Half of those people who were infected are now recovered. Only 1, I was going to write recovered here. Only 1 is infected. And I have 15 people recovered. Beautiful. Now what would happen after that? I would start dividing people in half, but I don't want to do that today. So we're going to leave it at there. So we went from 100 people, 100% infected, 16 people infected, to only 1 infected, always dividing the number of people infected by half. That is the concept of half-life. So over here, I used a day as my half-life. I'm going to get a new marker to write that in. Okay, so this is 1 half-life. 1 half-life has gone by in my first scenario where I had half of my people recovering in my first scenario. And then another half-life happened. So this is another half-life in which half of the people in this scenario recovered. If I add these 2 together, I'm going to get 1 half-life. 2 half-lives have gone by. 3 half-lives, 4 half-lives, etc. So my half-life in this scenario is considered 1 day. 2 half-lives later would be 2 days. 3 half-lives later would be 4 days. 3 days, and 4 half-lives later would be 4 days later. So going from this scenario all the way here, 4 half-lives later, 4 days later, I only get 1 person infected. So now let's tie this back into carbon-14 and other atoms that are radioactive. for earth science, one of the most important atoms you're going to want to know about is carbon-14. This is in your reference table right here. Carbon-14 is written this way. It's written with C for carbon and the 14 up here, exactly the way it's written in your reference table. And then in your reference table, there's an arrow saying that carbon-14 turns into nitrogen-14. And before you think that you can turn gold into lead, this is not this scenario. Carbon-14 can turn into nitrogen because carbon-14 happens to have 6 protons. Those are the red spheres that I tried to draw here. 6 protons and 8 neutrons. So if you remember anything from 8th grade, you're going to know that's two neutrons too many. Carbon usually should have like 6 protons, 6 neutrons, 6 electrons. That would make it a very good carbon. This is being a bad carbon. It's a radioactive carbon. It has 2 neutrons too many. So what's going to happen is that one of these neutrons is going to decay and maybe turn into a proton by releasing energy. So what it's going to do is turn into, we're going to cross off one of these little neutrons, and we're going to pop an extra, make this, give it an extra proton, and now it has 7 protons. 7 protons, that's not carbon anymore, that's nitrogen. So the carbon-14, it disintegrates, its radioactive product is going to be nitrogen-14. That's how it happens. In your earth science reference table, it says that 1 half-life of carbon-14 is 5.7 times 10 to the 3rd power. Okay, so what does that actually mean? That means that that half-life is 5,700 years. So going back to my half-life scenario, that means that 1 half-life that I said was like 1 day is going to take 5,700 years. And then for half of those carbon-14s that are remaining, it'll take 5,700 years more to decay half of it. So now going back to my scenario, replacing carbon-14. In my first scenario that I said, I had 16 people in a hospital that were infected with coronavirus. Now I have 16 radioactive atoms, carbon-14 atoms, in a box. 16 carbon-14 atoms in a box. They're radioactive. They want to turn into nitrogen, but not all of them do. It's random. I'm going to randomly select 8 of them, half of them, to disintegrate into nitrogen-14. So half of them do, and that takes 5,700 years to do so. After that, it takes another 5,700 years for those remaining carbon-14. Oops, sorry, Bella. You scared her. It takes another 5,700 years for us to turn half of what was left, half the carbon-14 that was left, into nitrogen-14. And then over here in this scenario, lift this up a little bit, it's going to take another 5,700 years for half of the carbon to disintegrate even more. And in the very, very end, I'm only left with 1 carbon-14 atom after all this time. So if I were to add up, if I were to know how long it would take after 4 half-lives to go from 16, let's say 16 grams of carbon-14 all the way to 1 gram of carbon-14. How long would that take to go from 16 grams all the way down to 1 gram? Well, let's find out. Over here, 1 half-life took 5,700 days. Another half-life took 5,700 years. Sorry, this was years. So right now, 2 half-lives took, let's add them together, 5,700 plus 5,700. and I'm going to get 11,400. Okay, so 2 half-lives to go from 16 grams of carbon-14 to 8 grams took 11,400 years. 3 half-lives. I'm going to take the 11,400 years that I had and add another 5,700 to figure out how many 3 half-lives are worth. So I got 0, 0, 1, 1, and I get 17,100 years. Now that's starting to be a long time. All right, so another half-life later. Let's see how long. 4 half-lives later, I'm going to take this number, 17,100. Can you see that? Hopefully. Hey, good girl. I'm going to take 17,000. I love you too. It's your breakfast time, I know. 17,100 plus 5,700. And you're going to get 22,800 years is the time it's going to take for it to go under 4 half-lives. So from 16 to 8 to 4 to 2 to 1. 4 half-lives later. All right. Questions. I know this is a tough topic. You can drop questions below. Please feel free to pause the video, rewind the video, rewatch the video, ask me questions about the video, and make me explain everything again. Because right now I'm just going to keep the ball rolling. Normally in class I would stop right here, but since I'm going to try to condense everything, we're going to graph. So at this point you should really have paused the video to make sure you understand it before going on. But I'm going to keep going on because I want to keep everything all together. Okay, so we're going to attempt to graph this monster. And I drew an axis here. Okay, so let's do a graph. And on my y-axis, I want to put, what do I want to put today? I want to put grams of carbon-14. I think it's going to be easier to put numbers today. So I want to put grams of carbon-14. And in my bottom axis, I want to put time. And time I'm going to label, today I'm going to do years. Today I'm going to do years. I'm going to do more graphs later on, but today I'm going to keep it simple. Okay, so after 1 half-life, that is 5,700 years. I'm going to have to erase this so your little head's not in the way. After 5,700 years, we're going to get how many grams of carbon-14? We're going to end up with only 8. So I started with 16 at my 0 point. This is 0. I started with 16. Now I'm going to go to half, which would be right here. Okay, after another 5,700 years, so now we're at 11,000. We're at 11,000, what did I say here? 11,400. 11,400. Hello. You're so cute. I am going to only have 4. So again, in half, I only have 4. And after 17,100 years, 17,100, I would only end up with 2. And after 22,800, I'm going to end up with 1. So what you're going to get here is an exponential curve, which hopefully is going to look like the exponential decline of the coronavirus as people start to recover and we start to get herd immunity, which I could talk about forever, but I'm not going to because today's topic is carbon-14. So people do the right thing, stay at home, don't infect other people. If you are infected, the good news is that you will develop some sort of immunity and you'll stop infecting. After you recover, you don't carry it anymore, you don't infect new people with it. Hopefully, they're still finding out new information about this. So hopefully when people start to get immune to it, that's when the lockdown will end and then we can start going outside again. All right, so ask me questions. There's a brief cast learning based on this information right here. It's on page 1 of your reference table, the front cover of it. If you have questions, please ask me. I'll be here from 8 to 9. All right. Have a great day. Enjoy the snow. Go outside to enjoy the snow and enjoy.